welcome to the next topic on our embedded system cars. So today topic we will have the discussion or presentation on preemptive operating systems. So our chapter operating system, and today we will discuss about preemptive operating system, and we'll see what is the difference between what we discussed last time about the sequential or non-preemptive operating system. The main difference from the preemptive operating systems and the non-preemptive operating system is that preemptive or non-preemptive operating systems are not allowing us to interrupt the task, and usually the task should release the control on the processor by itself. That means it should return and leave the processor to other tasks. Yeah, preemptive operating systems are the tasks that are allowing, let's say like this, to be interrupted, and after we'll continue the execution when the when the operating system will give them back the processor. Yeah, so let's start similar to the last time, or like in the previous lecture, that with the assumption that an operating system is in a system that is managing the resources of an how to say processing unit, let's say. Okay, so now what are the resources? Resources are memory, peripheral models, and processing time. This is, as general rules, are well known, so I don't think that you are not familiar with that, because most probably you already have this assumption or this discussion on other courses. Yeah, but just raise your hand if you heard about that and you are familiar with this assumption. Okay, thank you for involving here in our discussion. I want that to be more interactive with the how to say the methods that we have. Okay, so we have three kind of resources: memory, peripheral models, and processing time. Yeah, of course we have a memory manager for the memory, and we have here a kind of scheduler for the managing the processing time, and of course we have service or drivers for peripheral devices. Yeah, but let's start from the same story, or a kind of, let's say, we'll have a tale or a story about the operating system. So first of all, let's start from the same point that let's assume that we have a single process program that in our case, or in the embedded system, usually is running on an infinite loop. Yeah, what that means, this infinite loop is has some mechanisms or features that is collecting the data from the input, yeah, processing it infinitely, and provide some results or outputs. Yeah, and the most the simplest application that we can develop for a microcontroller or an embedded system is, okay, of course, toggle LED. This is the hello world, let's say like this, for a microcontroller, or the entry level for the microcontroller. So usually we are checking if the button is pressed, and depending if the button is pressed, it is toggling for if it is on, then off, or vice versa. Yeah. After that, we are waiting for release of the button. Why? because if not, in this case, most probably this delay will be too short and will catch another button pressed state. This is why we should wait first for the pressing and waiting for the release in order to be able to detect the next pushing. Not the status of the press, but the push button. Okay, and usually in microcontroller we have this kind of behavior when in the initial state we have the setup is the place where we are initiating all the drivers, memory, other things that we want to run only once at the begin, but we have continuous loop and the let's say the processing itself, that is usually performed in the infinite loop. Okay, so initialize, we are initializing the system, and after that we are running, or run in the an infinite loop. This is the main application. It's let's say the simplest application we can develop. Maybe even simpler we can do. But this is a kind of an interactive application, because the simplest is just toggle LED. In this case, it's toggling only if we request it by pressing button. This is how we will interact. Let's say we have a kind of simplest binary sensor and simplest binary actuator. Now, let's see. This is the entry point to our topic, today topic. But let's assume that we have many buttons, not only one button. Okay, and let's see the problem. And we already defined the problem that here we have a spin lock. And what is the problem of this spin lock? Okay, in the situation that where we have only one button, one LED, and one LED, okay, it is not a problem. But what if we have many buttons? We have, let's say, here a button, a bumper button, that is waiting for pressing, after that waiting for release. We have second button. We have something different, okay, not button, but a sensor here, or a line sensor, okay? We have some application that is doing something in order to manage, let's say here, this wheel control. Wheel control usually will have here some, let's say, holes, and this sensor will wait for the hole. After that, we'll increment and we'll check the time at one point, second point, and also we'll, let's say, we can have here a kind of spin lock. And we already defined a method how to build application without taking in account, but it's not so easy, because in our case we would like to not take in account every single point where is the probability to have a spin lock and so on. Maybe there are other mechanisms to detect other spin locks and something like that. It's general proposed methods that can be found in the other references. But we would like to do normal programming, because the sequential system or the non-preemptive system that we defined in the last in the previous example of the operating system, sequential operating system, we should take in account and to avoid the spin lock, because it is because of the nature of the operating system, it is not supporting them. But we know, and starting with our first steps in programming, we want to be free in our application and so on. So we would like to define some applications that are running in parallel, similar to our to the application that are running usually on a normal PC. Because okay, of course you can define many applications. Let's see, here, yeah, we have a lot of applications that are running in parallel, and no one is disturbing another from its functionality, and we would like to have the same. Yes, this is the right approach, let's say, to have an application run on operating system. Yeah. Okay, let's see how we can do that. But the story is will start from multitasking but defined by a single inside of a single process. Okay, we have three, let's say, tasks, and usually when we have this approach, we have a power on, it's starting, it's initializing everything, and start. Okay, we have the first job or the first task, it's doing. After that, the task B will wait until the task A will release the processor. In this case, we can say that this is non-preemptive. Why? Because we cannot interrupt task A. We will wait until the task A will release back the control on the processor. Yeah. So non-preemptive means non-interruptible task or application. By the way, I just want now to ask you, did you hear about the principle preemptive and the non-preemptive, another courses to see what is the, if you have some eventual primary knowledge on this topic? Did you hear about the preemption? Okay, nice. Somebody yes, others? Okay, then that will be easiest now to explain, to not go in detail about the preemption. Just assume, we are assuming that non-preemptive, that is the task that is that tasks that are not interruptible. Preemptive, interruptible task. Okay, now we will see that the task B will be executed only after the task A will release the processing time unit, yeah, or the processing time resource. So now, but we would like to have something like this, because we have here a continuous loop. We want to run three tasks, but we would like to have them in parallel. Yeah, we want to have one problem solved in one application. We want the second problem in a second application, and the third, of course, is the third application. Three buttons in parallel, let's say like this. How we can do that? And yes, in this case, this one will be the first task, let's say, the second, and the third. Yeah. Okay. As it is on this slide, we can say that, okay, I can have three microcontrollers in parallel, and I can run three applications in parallel. Yes, another approach could be that, okay, we can buy an tri-core microcontroller. By the way, there are some microcontrollers with 3 cores, okay, or tri-core, and we can start on every processor. We can give an entry point to the program, and the processor and the processing unit will walk, let's say like this, every one on its own task. Yeah, so why not? But the reality is that usually we have many applications or many tasks than the number of the processors. So in this case, we would like to have a method that is allowing us to do multitasking, yeah, on single processor. How we can do that? Okay, the secret consists in the following. We should understand very, very good what is the process of calling a function. By the way, Do you know what's happening on calling a function? Let's imagine we have this program. Okay, this is the main function, and we have a subroutine or function that will be invoked or called inside of the main program. Yeah, what will happen? Yeah, okay, we will have like this. We have the main thread, and here we have the call task A. So what will happen here? The control will be transferred to the task A. Yeah, so the processor will be under control of the task A until we will reach the end and the return instruction, or in assembly it will be a kind of ret. Yeah, and here we'll have a kind of call task A from assembly point of view. Yeah, because okay, every program in C is compiled, and finally we'll have assembly language instruction or binary. Okay, but what is happening when behind or inside of the processor when we call a function? But this is the very important. Most probably already heard about that, but I would like to give some explanation, because this is the main thing that is staying on the basis of multitasking. Yeah. So we have the main function. We reach this point, and at this point we call the function. What's happening? Usually we have behind of the call function, we have a jump. Yeah? But this jump is not just a jump as usually we have, let's say, go to the certain address. We have in parallel, or first, before jumping, we are storing. Okay, we are it is automatically calling the push of instruction of the program counter that is storing somewhere in the stack, yeah, at the address of the stack pointer. But it's very important, at the address where the stack point the stack pointer is placed, or let's say is indicating. Yeah, so first of all, but we are storing not the address of the current address of the program counter, but we are storing the next address of the next instruction. So we are storing here my sub plus one instruction. It's not plus one in address, because I don't know if we have 42 bit system or 64 and so on, and most probably the instruction will have many more than one address, but we are storing the address of the next instruction in the stack. Why? Because after we are jumping here, we are executing this function, we meet the return, and this return is doing an vice versa operating before going back, or how it's going back, or what means to have the return function. It's very easy. We are recovering back. Okay, by the way, I forgot to say one very important thing. In the moment I'm storing the address of the next instruction here, yeah, automatically the stack pointer will go to a new address. Why? To be ready to another call function or another stack storing. Yeah, but when we let's say we are not using anymore the stack inside of this function, and we reach the return function. Okay, we are reaching the return function, and this case will have automatically a pop. What means pop program counter? Means that the stack pointer will go back to the address where we stored last time and update the program counter with the address that is stored here. This is how we know where to go back, because most probably we'll have another call here of my function. Yeah, in this case, the already we will store not this address but the next address of the next instruction of the second call. Yeah, and it will be stored here, go from here to this function, execute it, and go back here already. Why? Because we stored the returning address in the stack. Yeah. Now, just a quick check. I would like to know the level of understanding from 0 to 5 to 10, let's say like this, of level of understanding how the the process of calling a function is working actually. Is the question, do you understand how the program or how the a calling function is executed? It's very important, yeah, because if you don't, then it's not, we don't have a reason to go further, because everything is based exactly in on this principle. I most probably already know from other courses, but it's very important now. We are learning in case we would like to build an multitask operating system, how we will proceed, how we will do that. Okay, thank you. Please, others, because I want more of you to be involved in our discussions, and I would like to see a general feedback. Okay, thank you. I see 7, 8, 10, and many marks. Thank you. It's good enough. Okay, 10 as theory. It's not in theory, it's practically, because okay, maybe if someone is more interested in this process, we can even go into details and I can explain more, because personally I like this process, and the people or the people that developed this system had a lot of, let's say, intelligence in order to do so simple mechanism, and that is one of the base of the processing, let's say like this. Okay, so we should understand first of all how the stack is working, because stack is a mechanism that is storing the data, the data without taking in account where it is stored. How? We have a kind of stack point. We have a stack pointer. Once we push something, yeah, it's automatically moving on to the next location, but we are not taking in account that. This is a very interesting one. It's the stack is working, by the way, by the principle LIFO. Last in, first out. So last address stored will be the first address we get in order to update the program counter. Once updated, was program counter updated, that means we let's say give the address of execution, let's say. So once again, this is the general principle how subroutine is call is working. Now let's go further. How we can do? How we can proceed to have parallel processing? This is the formula, and this is the let's say the answer. First of all, let's have our here we have our main task. The main task meaning the setup and loop that we have, and we will consider that this continuous loop is exactly the idle process that we have here. Something that is doing when we don't need to use a processor. That means when nothing to do, it's staying here on this continuous loop. Okay, this is the first step. Yeah. The second step is we will define our continuous loop applications. Yeah, we have first task A, task B, task C that are running in continuous loop. Okay, so first one, second one, and third one. Now, what we should do here, we will define or we will, let's say, allocate for a memory area for everyone. We will allocate memory area for everyone. Yeah. For first task, just malloc. Allocate memory for task A, task B, task C. Why? Okay, here we have a mark. This is a stack. Also, we will define some temporary or a stack pointer, temporary location for a stack pointer for every task. Yeah, what we are doing, we are duplicating this principle. Yeah, we will have memory address and the context of the application and stack pointer. Yeah, stack pointer or address for the stack pointer and a stack, yeah, for every application. So taking into account that, what is that? So for everyone, we will have that. And this one, but not exactly this one, let's say, will remain allocated to the idle process. Okay, so we'll have the general, this, let's say this is the idle, and it will have all the memory, but somewhere in the heap we will create some context or virtual memory, let's say like this, a virtual space for every task. Yeah, okay. So now let's say we have an power on reset. Yeah, we have here. And we will go into the main process. Okay, we will have the power on reset. Yeah. Power on reset. It's starting, but in parallel, we have this piece of code, let's say, or interruption service routine that, let's say, we will have 1 millisecond, or we can say that it is a system tick. Yeah. So this interruption will occur once per system tick. We will define for some applications it could be 1 millisecond, but for other it could be microsecond or it could be 10 milliseconds. Why not? Depends of what. And here we have the CPU. CPU, and this is the hardware. Yeah, this is the hardware and hardware stack pointer. Those that we have here are just the stack pointers, but the copy of that. Why? To have a kind of context of an application. So the real one is here. So now in this system tick, we will define a scheduler that is deciding or is managing the let's say which application will run in the processor. So now we have the power on reset, and it's starting from executing the main function. Okay, so at some moment or at certain moment we have the interruption service routine execution. That means the control will interrupt the idle process and will go here. Now this schedule, okay, according to the round robin, will decide who is which task is the next to be selected. Okay, let's say that this round robin, okay, that is round robin means the next from round, yeah, it is deciding that the next task is A. Okay, so what it will do? It will now what we have stack pointer now is showing or it's indicating to the stack, to the main stack. Yeah. Why? Because it's interrupted and we have a kind of hardware call of a function. Hardware call. What means hardware call? That means we don't have an explicit call of the function. We have an event, and event automatically is calling, but the execution anyway is interrupted to go to the, let's say, ISR. Now, inside of this ISR, what will happen? In this stack pointer, we will store the address from here, because it was interrupted here, so the return address will stay here. Now, scheduler, what scheduler is doing? Is deciding which task will be the next that will be executed. It decided, let's say, it's task A. Okay, task A. Remember, now scheduler, what is doing the next? It's storing this value here and is bringing the stack pointer from here. Now, when getting out from the interrupt service routine, it will extract from where the returning address. Of course, by the stack pointer, but now look, we change it, we store this address here and take the address that's indicating to the stack of the task A. So it's going from here to the scheduler and not going back to the idle process, but it's going to the task A. Yeah, so it's will not return it here, but will return here. Let me make some clean. So first of all, what is doing? So selecting task A and decide we would like to change from idle to task A. In this case, we will store this here and we'll bring the stack pointer here. So first one. So one. Okay. This is the free what we are doing. Changing the stack pointer will, in this case, we will have the returning address that is registered to the task A. Okay. Now let's say, and first step, second step. Now that means we changed the context and we transfer the control from the idle process to the A. Now let's play another scenario. Let's imagine that now we have the task A that is executing. Yeah, we have task A in execution, and we have here an event. So system tick say that okay, enough task A, and what we'll do? We'll have here an interruption, and we'll go to the SR. Now the scheduler will, according to the round, that task B is the next. So what we will do? We will store back the stack pointer here in order to remember where we where to task A from which point on which point it stopped and should continue the next time, and bring the stack pointer from task B here. Now, when we will go out, we will go here. So it was interrupted here. Go to interruption to the scheduler. Yeah, scheduler switched the context by changing the stack pointer, and when we are going back, will go back according to this stack pointer. So at the point where it last time it was interrupted by scheduler. So this is the main principle, how we are changing stack pointer or how we switch the context. Switching the context meaning to change the stack pointer in order to go to another memory area with the execution. So please now I would like to see here what is if you are with me or not. Yeah. So please, the level of understanding how the switch context is working, please give me a mark or a note, some feedbacks, the level of understanding the principle. Thank you. Thank you. I see you are already, most probably already familiar. Raise your hand if you were familiar with this principle or who was familiar with the principle of changing and switching context. Okay, most probably already had this, but it's very important, and for me that was surprising because I was in the situation to go deep inside of a microcontroller and even wanted to develop a operating system for that. But first of all, okay, we are changing the context, but most probably we have the task was interrupted at the moment when it was in the process of performing A equal B plus C. Most probably for B and C, it was using some general proposed registers, and at the moment it was interrupted, some data still are in the general proposed register, and because of switching context, those registers will be overwritten by another data, and when it will come back somewhere to continue the evaluation. Where's my pointer? Okay, to continue evaluation of B plus C, but who knows, maybe it stopped somewhere in the middle where, I don't know, because B and C could be some long, let's say, type, and in this case, it's doing this addition by portion, let's say the first byte, second byte, third byte, and so on. And the most probably, as the other task already overwritten the register, it will not find its own data in the register. This is why the scheduler is doing something more. It's not changing the stack pointer only, but first it is storing, let's say, before changing, before storing the stack pointer, it first storing the general proposed register in the stack here. Yeah. After that, storing the stack pointer, and only after it is changing the stack pointer. Okay, changing the stack pointer, that means, okay, we already switch it to another memory area. So after changing that, it's restoring the general proposed register related to the another task. Yeah, in order to this task to be able to continue from the point and the context of the registers that it was interrupted. So now the complete story of the switching context is, first, when the interruption occurs, it is storing the general proposed register, make an arbitration and decide which of the tasks will be the next. After deciding, it is changing the stack pointer and automatically switch the context. And after switching the context, it is restoring the second task, yeah, or the target task general purpose register. Okay, as simple as that. So this is the whole story of the switching context. Store current state of, but not only general purpose register. There are many artifacts, but this is the general idea. Store the current state, select the next task, change or switch the context, restore back the register, okay, in another context. Okay, so this is the whole story, and now let's see what a multitasking is according, or to have some comparison between the preemptive and non-preemptive operating system. Because preemptive system means that task B will be executed only after releasing the control from the task A, and task A should release it by himself. In the preemptive operating system, we have many tasks, but those tasks could be interrupted. And the scheduler, in our case, is forcing the task to leave the control. But from the point of view of the order of execution, nothing changes. Here we have to define task A, B, and C, and to plan the process, the release of the control on the processor. Okay, I'm back. So here we have to plan where is the point where we are releasing the control of the processor. Okay, task A should be defined, let's say, smart, yeah, in order to avoid spin lock, to have execution sequentially, and so on. Here, we don't have anymore this problem, yeah. And yes, this is from our point of view, from the execution point of view, is better to have this approach. But this approach means to have, let's say, additional memory for the operating system. Yeah? And we have limitation of the memory per task, because for this one, for non-preemptive, for non-preemptive, according to this scheme at least, we have the whole memory accessible by the task A, and in the second case, we have only the context it is allocated. Okay, we have allocated some task, let's say 1 kilobyte or 2, or doesn't matter how much, but we should split the memory between tasks. Yeah. So let's have another things very interesting, the task delay. And why we are going here? Because let's say that we have a special task, but not always we have to do something. Yeah, because doing something, that means every task need processing time. But let's imagine that we are performing some execution, yeah, but not, we need to do this execution once in, I don't know, in 1 second, once in a year, once in a month. So, and the rest of the time it should somehow delay or sleep or something like that. Yeah, so we can use this delay not to do, not to not do, or how to say, not to do nothing, but even to not do anything. Yeah. So what we can do, we can release the processor and inform the scheduler to not select the task A, B, or C during this delay. So how we can do that? Very simple. We can, similar to the non-preemptive operating system, for the delay, we will put a counter, yeah, and we will develop the arbiter so that it will select or will arbiter it will make arbitration only between tasks or that are not in the delay. That means that this counter already reached the 0, yeah, or less. So in this case, this arbiter will select only the task that is ready to be executed, is not staying in a suspension or waiting something. Yeah. So in this case, in case any task is on delay, it will not be selected. So the scheduler will return us the ID of the task that should be selected, and it's not in the delay. But after that, in case, let's say this is the real operating system or the switch context, yeah. So in case if or when the arbiter decided to have, let's say, task A ID, yeah, it will select the next stack pointer, the stack pointer of the task A. Yeah, this one. Okay, so after we will change by this function the stack pointer, and it will go and will continue execution to the task A. Yeah. So what is the result of this optimization? Yeah? That means, let's say that all the tasks should perform some execution. So now we have this area. So task A, round robin, task B, round robin will decide that, okay, the next task, and so on in a round. But at a certain moment, task A decide, I would like to delay a little. Yeah? So now from this point, we'll have round robin, task A, B, C, B, C, yeah? And so on. At a certain moment, task B decided, I will wait a little, I don't need a processor. In this case, the whole processor will remain on the task C, but at a certain moment, even task C say, I don't need, I want to sleep. So what will happen then? Round robin will not have what to select, and it will select the stack pointer of the idle process. So that means doing nothing, do something that is in background. And then only in this case, we'll see the entry point is from idle. But once we have a task in execution on the queue, yeah, or a task that is ready to be selected, it will select a task. But only if we don't have anything, any task that is ready, that means all the counters are higher than 1, let's say higher than 0. In this case, we'll have something like this. Yeah? We will change the stack pointer from here. So we'll stay in the main task, okay, and the idle process. So we always will have a task that could be selected by default, the main. So at the certain moment, task A said, okay, my time to delay is end. So it will have the whole process. After that, when the task B also will finish its delay, we'll have 2 tasks and so on, 3 tasks, and back all the tasks are online or alive. So now please give me a feedback if you understand the idea of the delay, and the most important, why we should have this kind of delay, not just delay MS like in Arduino, because doing delay MS like in Arduino, we will do no operation. That means we always will be selected. But here, delay means inform the scheduler to not be selected during a certain period of time. And in this case, we release the processor to other tasks that needs or highly need asking for processing time. Thank you. Others? I need a 30 answers. I see here in my agenda that you are already at least 30. So please, everyone. Okay, so here is the only example. This is about the task delay, yeah, but we can have also some, let's say, semaphore, where not only this one could be let's say, a factor to be selected, but also we can have some blocking, or let's say one task is blocked to wait semaphore, and we will attach, let's say, an indicator to a pointer, a semaphore that is not null. So in case we released, in this case we'll put null, and this will be another let's say check for be blocked. So in this case it could be blocked by a delay, or some expecting some information and something like that. So, but this is only a simple example how we are doing, we are performing the delay, but the event or this check could be not only a delay, but also a kind of a pointer to something. And in case we don't have allocated or are not setting the pointer, or the pointer is released, in this case we can continue. Okay, the block could be not only the delay but other events. We'll see how. But let's see. We of course can try to build our own operating system. Let's see. We have here the actually this one, the timer, and usually now the microcontroller usually have already built in system time, sys tick timer. And even on your microcontroller, most probably on your PC, you have this system tick timer, especially for that, not for PVM purpose or input capture, that is specially defined for operating system, on which the Windows, Linux, or FreeRTOS, let's say, is working on. Yeah? And let's say what is here, we can say that this is operating system, or let's say scheduler, because operating system has many managers. In our case, scheduler is manager of the processing time, and we have memory manager for memory allocation, and we have drivers for peripheral models operation. So the scheduler, even on Windows or Linux, let's say we can assume that it's working like in this concept, but more maybe something different, but this is the main concept how it can be done. But we'll not go deep inside. It's just an example how we can build an operating system, and we see that an operating system can be defined in a few lines of code, even a preemptive system. Okay, so of course, you are familiar with Windows and Linux that are preemptive operating system, but for microcontroller or for the small microcontroller, most probably Windows or Linux will not fit it, or will not fit the requirements, minimal requirements of the microcontroller. But let's see how we can do. We will have a FreeRTOS, meaning free real-time operating system. Real-time means, by the way, does anybody know what means real-time? Can you provide me an real-time definition? Please. So real-time means the reaction of the system in a predefined time. So if we'll decide that this is real time, that means everything is happening until this one is real time. This one is already a violation of the real time. But there are some remarks that we can have a hard real time, let's say, and we can have a soft real time, because let's say we have two system ticks, and this one between two we can have a budget from another tick, but soft real time means we can change, but the total number is the same. In this case, we can say that we have soft real time. But real time means reaction in a predefined slot of time. This is the short definition. Let's go further. Now let's see how we are building application using FreeRTOS, or real-time operating system. Of course, let's see. We would like to have, or let me go back. We would like to have that. We would like to have many applications that from their own point of view, they have everything they need and they're not interrupted. Even they are interrupted here inside of the application, it is not realizing that it's even interrupting because it's going back. Okay, it's going to the another task, but it's coming back in the same point. So in this case, from the point of view of continuity of the task, it remained the same. So we need many continuous loop in parallel. This is the principle. Okay. And now let's see. We will define a task. And we'll see this is the task. We see here up to this point the setup. And here we will be more attentive. We'll have here 4 semicolon, and to this point, this is the for context. We can even ignore that because just for the example proposal, and we'll see that from this point it's going back. So what we have here, we have an continuous loop task. Here is the same, is the second task. But let's define our own task that will be compatible with this one. Let's say now I'll try to draw with this pointer. I'll have task. Let's say this is task 1, task 2. Let's say task A. Okay, returning is void. Task A, and let's see this what is this parameter. This is mandatory parameter, but it is related somehow to argc, argv. By the way, did you use ever the argc, argv parameters for the main function? Who used, please just raise your hand. You can even connect voice and say why you use that. For what proposal? Okay, the argc, argv is the way you can transfer parameters to the application. So in case you have, let's say, app.exe, you can run it, or you can run app.exe. After that, you can put by the end, at the end, you can send parameter, let's say, from the command line. So here it's a kind of argc, argv, the way you can transfer to the application parameters. Why? When you are running or starting this task, you can transfer to the task something. usually is not used, but when you need. So now we have some setup. Okay, we'll say, see here some setup. But at a certain moment, we will need a continuous loop. Okay, I will define it another way, while one, and we will have here continuous loop. Okay, this function is similar to this one, just simple. Now this is setup, and this is loop. Okay, so now we see that we in the FreeRTOS, our task will be defined same way as main function, but we will not use the main, because main we can have in one application, we can have only one main. We'll have task A. Of course, the requirements are to have these parameters. Even we are not using them, we should have this prototype defined. Internally, usually it's just prohibited or even casted in order to not have warning even. You'll see that in the examples of code that you'll use with FreeRTOS. Yeah, but this is a mandatory parameter. But we have the name, that's all, and inside we should have a continuous loop. Okay. Now, how we launch tasks, those parallel tasks? Very simple. Now we will need a task create function that we will start it in the setup loop. We launch our task. After that, launch the operating system. Task scheduler. Start scheduler. Yeah, we are starting up. But before starting scheduler, we need to initiate our task. So now, very interesting or very important. Let's see what we have here. Here we have the name of the task first. We transfer the reference to the task create, which task second. We have this parameter is the string name that we can give to a task in order to, when we are debugging, we can find it where it is in the stack. Yeah, we are looking to the memory map and we can see, okay, this task is here. Okay, the third is how much memory we are allocating to the this task. Yeah, here we are allocating 1000 bytes. What that means, this one will be 1000. Okay, next we'll have null. What is that? That is the this parameter. Yeah, task parameter. If you want to transfer the parameters inside the task, this one should be transferred via this parameter. We have some structure and we want to send it back. Why here we have void in order to cast to any type of function. If we would like to use some int, we will put here, of course, int, but here we'll have recast back to the int and here cast to the void. Yeah. Now, this one is priority. Okay, it's strongly recommended to have same priority for all the tasks in order to have same priority when to have the same priority when it is selected by their own round robin arbiter. Otherwise, the scheduler will select the task with highest priority. And in case we will have only one task with highest priority, others will be at the lowest one, lower one. So the task with highest priority will use all the time because it will be always selected as the highest priority task that is requesting the processing time. So it's a kind of, I don't know, did you play with that or not? But let's see, we will put here some priority. Yeah, and I can change priority to real time, that means the highest priority, and to low priority. In case I will put the low priority, it will never be selected. Okay, in Windows maybe we have some smart manage in order to not leave the low priority never been executed, and to not leave the real time task to be executed always. Okay, anyway, I'll put, let's say I'll put this now in real time. In the older operating system like Windows 95 or maybe even XP, yeah, in case we put a real-time priority, usually the operating system start to freeze. Yeah, when we can do that? We can do that when we want something to use the all processing time for short period, and we know that this application will finish. Otherwise, you will freeze the whole your operating system. So the recommendation to keep always the same priority for all tasks. We will see the special example or special cases where we can raise the priority. Okay, now similar to the second, we see here the task name, task reference from here. Yeah, the string that we can in order to be able to locate it in the dump memory. The stack size, no parameter used. The priority is 1, and the last null is the task ID. Do you remember we have here the task ID that we could reference, and we have, of course, everything mapped on this ID. Yeah. So this way we can just select the ID and to kill the task, like a kind of, let's say we can do it by here. Yeah, I can just end any task I want. Why? Because I have this okay, this task ID, process ID. So here we can give let's say a structure or something like that in order to have this task ID stored on the special function, special data structure. So now we created 2 tasks and started operating system, let's say, with those 2 tasks. So now please give me some feedbacks in order to see if you understand how to start or how to set up an operating system to work with 2 tasks. Define task, create task, start operating system. 3 steps, no more. Even empty task, you can just, as I define it here, dummy task. Yeah. Please, waiting for your feedback because I want to continue and will go a little deeper with some details about the FreeRTOS. Of course, on the laboratory work, you will not be involved, or you don't have to define a preemptive operating system, but you'll have to use this FreeRTOS in order to define or to work with your application. And further, in the future, you will use only on laboratory works only operating system. This is a constraint. 2 main functions similar, just usually how I do. Usually when I'm using FreeRTOS operating system, I build an application. After that, rename the function main and start it from an operating system. So separately, I'm defining the application. After that, when I want to port an application from one microcontroller to another under the FreeRTOS, I just rename the function main to the task A, task B, task C, and just start it, allocate the memory, put the priority, start it. That's all. It's very simple. And today, by the way, in the next practice, I will demonstrate that. So let's go. Now, do you remember we have the running and not running state of the task. Running meaning that is now running on the processor. Otherwise, it's not selected. Okay, the running when the task is the state when the task is selected by the scheduler to be executed and it is on execution. Running means on execution. Not running, we can have three states. It's ready to be selected first. It's blocked, let's say by delay, or suspended. Let's say we by the ID we said to this suspend or stop. So when it's stopped, this is excluded from the arbitration. When it is delay or blocked, it will not be selected because it is blocked by, let's say in our case, delay, but we will see that we can have other events, and I will show you in the next slides. So it can be blocked by delaying, so not sleeping, delaying. It could be ready for execution. So in this case, it will stay in the round robin arbiter. Yeah, or it could be suspended. Even it's removed from the round robin arbitration at all until we somehow will say task resume. Yeah? And in case we will say task resume, in this case, other task, this task can be can be back to be to participate in the arbitration. Okay. So now it's the similar that I just extracted some diagrams, and we see we think that it's working like this. The task 1 is giving the control task B, task 1, task 2, and so on. But in the reality, it is task 1 is going to the kernel. Kernel give the control to task 2. Back to kernel, and so on. If task 1 is sleeping, we see that it's never selected, even not spend any microsecond or any one instruction to be involved in the task 1 execution. Just was not selected. Why? Because it's not ready or it's suspended. So now we see here something like that. We can say we have a task, yeah, and we have here the infinite loop. We have to print some string now, and we delay it for some milliseconds. Yeah, okay, we have here defined it. Yeah. So now this one is the time where we are not doing anything. Yeah, that means it will not be selected. So this is the task delay, the first type of suspending. Yeah, first type of blocking. So we have here first one, delay. Okay. Now another thing is inter-process communication. By the way, this is one of the main question, or most important question. Do you know what kind of inter-process communication, or how many types of inter-process communication you know? So one of them is semaphores. Yeah, semaphores, that means one process is giving a semaphore, that meaning is rising it, put in red, and second it's taking it. So the task is blocked by this function until someone will take it, and in this case, this is the case when we can raise the priority. Why? Because it's blocked by semaphore, and a task with lower priority is giving a semaphore and allowing the second task immediately to process it. So it will be immediately let's say, selected by the kernel because it's higher priority, and it will not stay in the queue in order to be selected. This is the case when we can raise the priority. When one lower priority task is giving, let's say in our case, semaphore, and it will take. Most probably on other application, on other material on the university curricula, most probably you already heard. By the way, just raise your hand. Did you hear about the semaphores? Okay, of course, yes, I'm sure that it was. But now lower your hand, and the next question will be, please lower your hand. Oh, nice, 70. Wow, how many people? Is it similar to what you see now on the screen or not? The principle. Some application is giving, another is taking. Most probably you already heard about the mutexes. And the semaphore, it's a type of mutex. Yeah? Because mutexes here and the application is built on semaphores. Okay, we'll have another IPC communication by queue. That means this task will receive, and if the queue is empty, it will be blocked by this function. That means it will stay in the block until in the queue we will have something. But we can say that it will wait, but we can set a kind of timeout for the waiting, okay? Because okay, I will not stay as a spin log because buffer, nothing is coming to the buffer. I can say, okay, I'll wait for a few seconds, but if nothing, I just will make some requests why I don't have nothing. And I can ask provider of the information, everything is okay? Ah, it's okay. So I go back to receive another. So in this case, it could be a kind of receiver, let's say, function for printf, for let's say string processor. And here we can have a CAN bus, we can see another task or human button, let's say, or a keyboard, and we are pushing the case in the queue, but from another side, we are, let's say, put the standard input output as the IO. Yeah? And in this case, we can have a kind of buffer filling from the keyboard by a real-time driver and so on, but we'll have a kind of not blocking to the hardware device, putting a buffer here, and by this delay, we will see, okay, it's I don't have anything from the keyboard, but I can say, let's check if the keyboard is still alive. Yeah. So another function, of course, is queue send to front. So in this case, it will send to front, and we'll have this is another kind of interprocess communication by queue. By the way, are you familiar with the interprocessor communication by queue? Just raise your hand. So most probably yes, but it's a kind of buffers. Yeah, one provider, it's not operating at the same frequency and the same time frame like with the consumer, and in this case, it's a kind of amortization, let's say, between two processes. Let's say this is providing information by bursts, kind of no information after that very fast, but this is not ready to process it too fast as the provider is transferring. It's taking information like this, but with small pieces. In this case, it's better to have this kind of architectural approach. So, how to install this? FreeRTOS or minimal FreeRTOS? Okay, we will need the operating system itself is built on free files, the tasks or scheduler, yeah, queue and list. Why list? We need list for the scheduling, yeah. And we have microcontroller specific, the port C, where we have exactly the general purpose register and stack changing, because every microcontroller is doing it on specific methods. Yeah, we have here heap, meaning the memory manager, where the one is the simplest, that we have only allocation without deallocation, and the most complex memory manager is 5, yeah, and we should include the proper heap method, because for the Arduino Uno, let's say, we can have only the one, because reallocation is not possible, because only the memory manager will take all the memory of the Arduino Uno. But for more powerful, let's say, like ESP32, we can use even the most powerful memory manager by allocation, reallocation, and sorting of the memory, excluding the gaps, and so on. So this is the complexity of the memory allocator. Of course, we are including another library and some compiler and architecture, but one of the main configuration is the FreeRTOS config, where we are defining the fine-tuning of the operating system. But most probably you are already scared, because where I will find those files. Just download the release from the freertos.org. But in case you are using, let's say, Arduino IDE, to install FreeRTOS means to install the FreeRTOS as a library in the IDE. After that, it will include it on your application. So what you need, include FreeRTOS.h and define your task and start them. That's all for how to use FreeRTOS operating system. So finally, we finished that. Now I would like the last feedback from your side, if that was the level of your understanding, and if you, let's say, it is interesting. So please, the level from 0 to 10, including 0, yeah. And that's all for today.